Hi boys and girls, this is lecture 3.7 in Unit 3. The topic, Related Rates, part 2 of a discussion begun in the previous lecture. On this first slide, I have re-listed the guidelines for solving related rates problems. Identify all given quantities and quantities to be determined. Write an equation relating those quantities given and unknowns. Using the chain rule, implicitly differentiate both sides of the equation with respect to time t, and then substitute into the resulting equation all known values and solve for the required unknown value. This lecture consists of 3 more related rates examples, starting with this one involving a moving bus. A bus moving at 60 miles per hour along a straight road passes under a hot air balloon rising vertically at 20 miles per hour. If the balloon is 1 mile up when the bus is directly below it, how fast is the distance between the bus and the balloon increasing 1 minute later? As you can see, a diagram has already been provided for us. And once again, we have a right triangle depicting the relationship between the quantities being discussed in this problem. This right triangle is a little different, however, in that the hypotenuse is not constant. It is also varying in this scenario. It represents the increasing distance between the rising hot air balloon and the traveling bus. However, the 3 links of the triangle are going to be connected by the Pythagorean theorem, as we have seen before. But in this case, all 3 links will be assigned variables. So this is going to look like this. X squared plus y squared equals z squared. All 3 quantities vary, therefore they all receive variables in the equation. The derivative will look like this: 2x dx dt plus 2y dy dt equals 2z dz dt. Notice there are 1, 2, 3, 4, 5, 6 variables in this equation. Therefore, to solve for any one variable, we will need 5 known quantities to substitute into the equation in order to find the unknown that we're looking for. Well, let's see what information was given in the problem. We see that a bus is moving at 60 miles per hour. In this case, that quantity is represented by dx dt. dx dt is 60. The balloon is rising vertically at 20 miles per hour, which means that dy dt is 20. We still need to know what x, y, and z are, and that information was not explicitly given to us. However, we see that at some point the bus was directly below the balloon. And at that point the balloon was 1 mile high. 1 minute later, the bus had moved to this position, and of course the balloon had moved as well. We can find what those distances are using the rates that were given. If the bus is traveling at 60 miles per hour, that means it's moving at 1 mile per minute. So from this position to this position, it had moved 1 mile. Therefore, x is 1. When the bus was directly below the balloon, the height of the balloon was 1. Since it's traveling at 20 miles per hour, that means the balloon is traveling 1/3 of a mile in a minute. So 1 plus 1/3 of a mile that the balloon traveled in that 1 minute means that now the height of the balloon is 4/3. 4/3 of a mile. We're still going to need to know what z is, so let's use the Pythagorean theorem to solve for it. X squared, which is 1, plus y squared, which is 4/3 quantity squared, equals z squared. 1 plus 16 over 9 equals z squared. 25 over 9 equals z squared, which means 5/3 is z. Now we have all of the quantities we need to be able to solve for our unknown. Let's plug them into the equation and get dz dt. This is going to be 2 times x, which is 1, times dx dt, which is 60, plus 2 times 4/3 times dy dt, which is 20, and that has to equal 2 times 5/3, which is z, times dz dt, our unknown. We have 120 plus 160 over 3 equals 10/3 dz dt. Now let's multiply both sides of the equation by 3 over 10 in order to isolate dz dt. That's going to give us 36 plus 16 equals dz dt, which means that the distance between the balloon and the bus is increasing at a rate of 52 miles per hour. All right, and that's the solution to the moving bus problem. In our second example, we're going to discuss a changing angle of elevation. A television camera at ground level, here it is filming the liftoff of a space shuttle, here, that is rising vertically according to the position equation s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the angle of elevation of the camera, shown in the figure, 10 seconds after liftoff. Well, once again, we are provided with a lovely diagram depicting this information. And once again, we can see that a right triangle was formed by the relationship between the quantities and variables being discussed. However, we are not going to use the Pythagorean theorem here. That would give us no information about an angle of the triangle. Instead, we're going to need to use a trigonometric ratio. Which one? Well, in reference to the angle that we have here, we'll be discussing the side opposite and the side adjacent, which means we're going to need the tangent ratio. In this scenario, which variables are constant and which ones are changing? As it happens, of course, the side opposite is changing as the rocket is rising, but the adjacent side will remain constant, because the distance between the launch pad and the camera is not going to change. Of course, the angle will also be changing as the rocket is rising. In fact, we're going to be looking for d theta dt, the change in the angle of elevation. So let's set up that equation and take the derivative. We're going to have the tangent of the angle theta is equal to s over 2,000. A variable because this distance is changing, and a constant because this distance is not changing. Let's rewrite this as tan theta equals 1 over 2,000 s, so that it's a coefficient, and now take the derivative. Secant squared theta d theta dt is equal to 1 over 2,000 ds dt. We have 1, 2, 3 variables. We are solving for d theta dt, so we're going to need information about theta and ds dt in order to get that information. In order to get more specific information about theta and s, I need to go back to the problem and discover what was given to me there. I was given a position equation which will tell me the height of the rocket at any time after liftoff, and I was also told that we're interested in the time 10 seconds after liftoff. So what was the height of the rocket 10 seconds after liftoff? If the position equation is s equals 50t squared, the position 10 seconds after liftoff would be given by 50 times 10 squared, or 5,000 feet. So at this moment in time, s is 5,000. Now we'll be able to find out what theta is at this moment in time as well. Using the tangent ratio, tan theta has to be 5,000 over 2,000. That means theta is approximately 1.19 radians. Now remember, I needed to know what theta was, and I also need to know what ds dt is in order to solve for d theta dt. I'm going to get ds dt from the position function as well by taking the derivative. Position is 50t squared. ds dt, which is the derivative with respect to time, would be 100t. At 10 seconds, ds dt will be 100 times 10, or 1,000 feet per second. So if that's ds dt and I have theta as well, I'll be able to use this information to finish solving the problem. Using the derivative equation that I developed, we'll have secant squared theta, which is 1.19 radians. d theta dt is our unknown, and that should equal 1 over 2,000 times ds dt, which is 1,000. To isolate d theta dt, I'll divide both sides by secant squared of 1.19. 1,000 over 2,000 is 0.5, so that means I'm going to have 0.5 over secant squared of 1.19. This comes out to be approximately 0.07 radians per second. So this angle is changing at a rate of 0.07 radians per second 10 seconds after liftoff. And that is the solution to the changing angle of elevation problem. In this last example, we're going to examine the changing volume of a cone. A small funnel in the shape of a cone is being emptied of a fluid at the rate of 12 centimeters per second. That's a change in volume. So volume is changing with respect to time at 12 cubic centimeters per second. The height of the funnel is 20 centimeters and the radius of the top is 4 centimeters. How fast is the fluid level dropping when the level stands 5 centimeters above the vertex of the cone? So as this fluid is draining out of the cone, at the moment that the height was 5, we take a picture and we're going to model the scenario when h is 5. The question is, how fast is the fluid level dropping? And that is a change in height. We're being asked for dh dt. The rate at which the height is changing at the moment h is 5. Now, what formula connects all of these things, height, radius, and volume of a cone? Chances are it's the volume of a cone formula. Thank goodness we have such a thing. But in this problem, we're going to reduce the number of variables in the formula before taking the derivative. Since the volume is changing, the radius is changing, and the height is changing, this would be a complicated derivative to take. We would need to use the product rule here. There would be 3 rates, several variables, and we can make this a simpler formula before we take the derivative. Why? Because they told us that the height of the cone is 20 and the radius at the top is 4. The relationship between the height and the radius is proportional all the way down. So r over h is always going to be proportional to 4 over 20. Using this proportion, we'll be able to rewrite radius in terms of height. That means r is equal to 1/5 h, always, which means we can substitute that value in for r in our volume formula, giving us a simpler formula to deal with. V is equal to 1/3 pi. Instead of r now, we're going to use 1/5 h squared and then times h. Let's simplify this. 1/5 squared is 1 over 25 times 1/3, 1 over 75 pi, and then we're going to have h cubed. Now let's take the derivative. The derivative of v is dv dt. 1 over 75 pi is a coefficient, and that will be multiplied by the derivative of h cubed, which is 3h squared dh dt. Let's simplify this as well. dv dt then will equal 3 times 1 over 75 is 3 over 75 pi h squared dh dt. Remember, we're solving for dh dt. All we need then is the height at this moment in time and the rate at which the volume is changing at this moment in time. Fortuitously, that is exactly the information we were given. So let's plug those values into our formula and solve for dH/dt. dV/dt is 12 equals 3 over 75 pi. H squared will be 25 dH/dt. 25 times 3 is 75, so this becomes 75 over 75, which is actually 1 times pi dH/dt, which means that dH/dt, the rate at which the height is changing when the height is 5, is 12 over pi centimeters per second. And that is the solution to the changing volume problem. That's it for today's lecture. I leave you with a stunning display of fractals and an inspiring mathematical quote by Mr. Polya. Beauty in mathematics is seeing the truth without effort. God bless you, boys and girls.